Hi, this is a video presentation from my group's final project for BME 595 Deep Learning. I will be talking about a generalized activity recognition network for the UCF101 dataset. Current neural network training methods only focus on obtaining the right prediction for an input. A network will learn to pick up on any discriminating features that allow it to provide the correct label for a sample in the training set. Unfortunately, this will result in a network that is not generalizable to unseen data. In terms of activity recognition in videos, the network may end up using background pixels to make decisions rather than the pixels where the activity is occurring. This can cause difficulties when passing in a new video of the same activity that is occurring with a different background. If the neural network instead uses the pixels where the activity is happening, then it is more likely to correctly classify an unseen video. Therefore, the network must be guided during training so that not only does it learn to discriminate between different classes, but that it also uses pixels and regions of motion to discriminate. This will reduce bias towards the data set, as the resulting network will not use any background features to make predictions. This guidance can be done by using a modified loss function so that the network is penalized when it uses background pixels instead of foreground pixels to produce an output. We will be using attention heat maps to assess which pixels contribute most to the prediction. We will use the GradCam method to generate these attention heat maps. A brief overview of how the GradCam method produces these heat maps. First, we select the layer in our neural network to visualize the heat maps. When we perform a forward pass on the input, we record the forward activations for that specific layer. Then we will back propagate using the neuron corresponding to the predicted class to obtain the gradients at that layer. Then we sum the gradients over each filter at that layer and use that sum as a weight to perform a linear combination of the activations. This linear combination will represent which pixels contributed the most to the output. Then we upsample these heat maps and overlay on the original video frames so we can observe which regions of the image were used to perform the prediction. So first, we trained the C3D neural network model on UCF101. The UCF101 dataset contains 13,320 videos divided into 101 activity classes. We took each video and split them into mini clips of 16 frames and fed these mini clips into the network with a batch size of 20. We trained the network for 15 epochs to achieve 100% training accuracy. The diagram below shows the architecture of the C3D model. As you can see, there are 8 convolutional layers for feature extraction, and then we have 2 fully connected layers at the end to perform classification. Then we used that C3D model as a pre-trained model to then fine-tune it with a new loss function. This loss function penalizes the model for using background pixels to make its prediction. So we used optical flow to generate binary maps of the regions of motion in the videos, and the loss function shown on the slide takes these binary maps and increases the loss if the gradients at the pixels where there is no motion is high. Then the network will hopefully train and learn to look at the regions of motion to make a decision on which class the input belongs to. Here are the resulting heat maps, and they show that training with the new loss function does create an improvement in the heat maps. Here are 4 examples of inputs and overlaid heat maps. As you can see, the leftmost image is simply the heat maps from the original C3D model. The middle image is using the right reasons loss function, and the rightmost image is the original image. As you can see in the right reasons heat maps, the heat is more focused on where the motion is happening. As you can see in the top left, there's more heat over the person's face, applying the makeup, instead of where in the original there's heat in like the background, kind of on the door. And especially on the bottom right, on the gymnast, there's only heat primarily on the gymnast, whereas in the original C3D model, there's heat all over. So as you can see, our goal was to create a more generalizable network that focuses on the regions of motion to make its predictions, and the heat maps show that we were successful in creating this network. Thank you.